Hello, everyone. So today we're going to continue our conversation on mixtures by focusing in on mixtures of liquids. And so in order to do this, what we're going to do is similarly to when we treated gases, we're really going to be focusing in on chemical potential. Because chemical potential, being a measure of Gibbs free energy of a mixture component, is really going to tell me a lot about the behavior of the individual components in a system. So when trying to tackle a mixture of liquids, this can be a little bit tricky because, as you notice, we don't have a lot of good expressions for the liquid phase. So one of our tricks here is actually going to be assuming will be to look at two volatile liquids. Because if I have two volatile liquids, I can then take a look at the gas species that will be in equilibrium with the corresponding liquid. And so as long as the gas and liquid are going to be in equilibrium, I know that the chemical potential of the liquid will be equal to the chemical potential of the gas. And then at this point, I know that the chemical potential of the gas can be given as the chemical potential of the gas at standard state, and RT times the natural log of the vapor pressure of A. Because again, this is a equilibrium species, so the partial pressure in this case is indeed going to be the vapor pressure of the system. And again, this will be for our actual system, which is fairly useful because now I've turned a metric of the chemical potential for my liquid in terms of components that I can treat a lot more easily, namely that of the gas. Now, in truth, we don't always want to make a relationship to the chemical potential of the gas itself. So let's go ahead and play around a little bit here and compare the chemical potential of our liquid with the chemical potential of the liquid if it was pure. So again, if there was no secondary component of B present. Well, if I ignore the presence of B, well, then I can do a similar thing. And the chemical potential of the liquid, again, is going to be the standard equal to the standard state chemical potential of the gas, plus essentially the correction for the gas pressure. But there is a notable difference here, because in my actual system, we're essentially using the measured vapor pressure. But for a pure liquid, this is going to be the vapor pressure of the pure liquid species. And so this can actually be fairly useful, as what we may have noticed is by looking at these equations, both of them contain the chemical potential of the gas at standard state, but more importantly, they also contain the chemical potential of our mixed liquid and my pure liquid, and two measurable qualities that can essentially relate these two. So what I can do is for both of these expressions, I'm going to isolate the chemical potential of the gas at standard state, move that over to the left, and for the mixed species, this can be given as the chemical potential of my liquid minus RT times the natural log of the vapor pressure of the mixed species. But this is also going to be equal to the chemical potential of the pure liquid minus RT of the natural log of the vapor pressure of the pure liquid. And so at this point, I now have a relationship in between the chemical potentials of the pure and mixed states. So what I can then do is, using this relation of chemical potentials, I can generate an expression that will isolate how I isolate the chemical potential of my mixed species, which again is what we're really after. Because if I know the chemical potential of my mixed species, I will be able to predict its behavior. And so we can do this by moving our vapor pressure term over to the other side, at which point I now have a relationship in between the two chemical potentials and essentially two pressure terms. And as you may know, when in doubt, you can go ahead and try and condense your terms, especially because they share the same prefactor of RT. And because I have essentially here natural log of the vapor pressure minus the natural log of the pure vapor pressure, I can then go ahead and treat the negative log of the pure vapor pressure as plus the natural log of 1 over the pure vapor pressure. So this generates an expression for the chemical potential of a mixed species being dependent on the chemical potential of the pure liquid species, which, by the way, you can often end up finding as present in literature values, and essentially a correction for the pressure given as the natural log of the vapor pressure of my component of interest in the mixed case, and its pure vapor pressure. Well, we can find again this in a table, and it turns out that we spent most of last chapter figuring out how I can determine the vapor pressure for a pure species. So this essentially just gives me a single value that I need to measure in order to get the chemical potential of the system. So in a general case, I can go ahead and determine the vapor pressure or the chemical potential of any volatile liquid simply by measuring its vapor pressure. So this is actually going to be an incredibly useful feature. By just measuring the vapor pressure of a mixture, I can exactly get information about its stability, which will give me a lot of information about its reactivity, which it can be very powerful when trying to describe reactive systems. But one of the problems with this is that it requires me to make a measurement of the gas phase, and not only of the gas phase over volatile liquid, it also requires me to let the system come to equilibrium, which again, for a lot of samples can take a little bit too much time. So generally, one of the things we're going to try and do is take this expression, which gives me the chemical potential of a mixture in terms of its vapor pressure, and try and actually replace this with a property of the liquid itself. So essentially, some piece of information that doesn't depend on the system being volatile, but instead just relies on some measurable property of the liquid or dissolved mixture itself. So at this point, we're going to be required to make a couple of approximations. So one of the first ones that we can often make is if the intermolecular forces of A and B are actually fairly similar, then what this essentially tells me is that, well, if B looks just like A to a molecule of A in the liquid phase, well, then it's going to show very similar it's going to behave very similarly. And essentially what we're going to run into is a dilution problem, where the vapor pressure of A coming off of solution will essentially be related to the mole fraction of A, again, times the vapor pressure of if it was just A. So one way of thinking about this is that if I have a system that's just pure A, then at this point, my mole fraction of A is just 1. So my vapor pressure is equal to the vapor pressure of pure A. So again, works fine. We can also take a look at the other end. So if I have a solution that is pure B, then my mole fraction of A is 0, and then correspondingly, there's nothing to evaporate, and my vapor pressure of A is also 0. So again, it makes sense under these extreme ends. But one of the other very powerful features of this is that it also means that the mole fraction of A is going to be related to the ratio of the vapor pressure of the mixture over the vapor pressure of the pure species, which is going to give us a very useful description of the chemical potential or free energy of the system, as it can more or less just be described as the chemical potential of the pure species plus our RT prefactor times the natural log of the ratio of the abundance of A. So again, if I have a pure species of A, then this value goes to 1 and the chemical potentials are equal. If I have a extremely dilute system, well, then this is going to be a natural log of a very small value. And that small value is going to make this entire term become very negative, further stabilizing the system. So this also has the added benefit of telling me that the more diluted the system is, the more the more chemically stable it becomes with a lower chemical potential, meaning it's going to be much harder for a low abundance species to interact, which again makes sense because we've stabilized it through entropy. It already has a lot of configurations it's adopting in the liquid phase, so it doesn't really want to do anything else. But one of the important parts of this Raoult's law is that it's making this assumption that the IMFs experienced by A are going to be the same as are the same in the mixture as it is in the pure species. And because of that, more or less what we're watching is this linear relationship. Because again, as if I have a 50% a mole fraction of 0.5, then I literally have half as much A that can evaporate. And this is really where kind of Raoult's law shines, is under these cases of similar IMFs, because then really what you have is a mixture that's naturally evaporating. It just happens that there's only half as much to evaporate, so we have half the vapor pressure. Kind of a very logically satisfying assumption. Because again, it doesn't behave any differently in the mixture as it would by itself. There's just less of it. Now, this actually is quite a special case because if these IMFs are similar, they form what's called an ideal solution. And this is essentially based on the idea that it behaves the same as a mixture as by itself, which is actually quite ideal. It's almost the mixture version of an ideal gas law, something you occasionally approach, but very rarely, that you often approach, but very rarely reach. And again, this all stems from the fact that as I reduce the concentration of, say, A, as I move down in mole fraction, I reduce the entropic gain of vaporization, stabilize my tendency to remain in the liquid phase, and again, reducing the vapor pressure of the system because I have less entropy to gain by evaporation, and thus my free energy of evaporation is less, and thus so will be my partial pressure, mapping my way through thermodynamics. But this actually leads us to a very important question. What's going to happen if the IMFs are different from A interacting with A or A interacting with B? And this actually ends up turning into quite a tricky little scenario. And more or less what ends up happening is the more that the IMFs are different, the more that Raoult's law is going to break down. And it can essentially break down in two ways. You can imagine that if say I have carbon disulfide in acetone, well, it turns out that carbon disulfide really doesn't like hanging out with acetone. So that the more acetone that's present, the more carbon disulfide says, hey, I don't want to be here. I'm gonna go ahead and get out of town, and it's gonna become more volatile. And this essentially is a fairly uniform scenario, that a system is going to behave most according to Raoult's law when it's the only thing present. So thus, carbon disulfide is going to behave closest to Raoult's law when it has the dominant mole fraction, and the same thing here for acetone. So as long as most of what you're seeing is yourself, well then Raoult's law holds fairly well because the only IMFs you see are your own IMFs, so you behave just the same in the mixture as you do it ideally. Now, unfortunately, for a lot of systems, this means by the time your mole fraction gets down to, say, 0.9, you may see a positive deviation from Raoult's law if you don't like who's around you and you want to get out of town, or a negative deviation if I'd much rather hang out with the other guy than I will myself. And we'll get into these issues a little bit later. But in general, the important idea is that because Raoult's law actually holds fairly well, if the majority of what you're seeing around you is yourself, it's actually a pretty good description of the chemical potential and the vapor pressure of a solvent system. Because when you're the majority of what's present, well, that's a good solvent. And so thus, Raoult's is a very good description for solvent systems, but it's going to break down pretty hard for solutes. Because by the time you're a solute, you have no IMFs that look like yourself. You're interacting with somebody who's different. So you may end up wanting to get out of town or hang around. It really depends on the scenario. So what we're going to need to do next time is develop a good model to describe what happens when you're not in the majority. Till then, take care.